Good afternoon. Thank you for coming. This is our, I forget, third or fourth lecture, whatever. Schedule has been changed around, but the speaker today is listed as the sixth speaker on the bulletin, but we had to change things around because of scheduling their schedules. So there was some confusion about the one speaker that we had to cancel, the second speaker. Now she has been rescheduled for 2 weeks from today. Okay. So she will be on the 26th of February, which is after the actual course ends. But we have added her back on because people wanted to really hear her too. So today's speaker, we are very fortunate to have Dr. Rajesh Khanna from the University of Florida. He earned a PhD in physiology from Toronto and then a master's in pharmacology and bachelor's in toxicology there too. After completing a Natural Sciences and Engineering Research Council of Canada and American Heart Association funded postdoctoral fellowship, well, you got two fellowships, that's great. Fellowship in Physiology and Molecular Biology at UCLA. He then completed a fellowship in Cellular and Molecular Biology back in Toronto. Currently, he's in Gainesville. He's the director of the Center for Advanced Pain Therapeutics and Research, which is the acronym of CAPToR. And before this role, he was assistant professor at Indiana University and served as professor at the University of Arizona and professor and director at the NYU Pain Research Center. His research is focused on developing non-opioid medications. He has taken lab-discovered non-opioid compounds from the bench to the doorstep of clinical trials. He has published over 240 papers and holds multiple patents aimed at delivering safe, effective relief to over 50 million Americans living with daily chronic pain. So he's going to talk to us today about some of these new medications. Rajesh, thank you for coming. Please welcome Rajesh Khanna.
I'm here to tell you about pain. This is very loud, I'm sorry. I will adjust it. Okay, wonderful. As long as you can hear me, I'm good. So I'm going to take you through a journey of pain, hopefully not cause any pain. How many of here have experienced some sort of chronic pain? See, that's terrible. I'm sorry for you. But I hope you have some way of dealing with. The problem with pain is, as you already know, it is really the great unifier. You may have all kinds of diseases, but one common pathology in all of them is pain. And so while it's not something that kills you, it really is killing you, right? It's what brings you to the hospital, to the doctor. So I think it's very important as a society to be able to deal with to develop and to have new options for folks that are suffering from chronic pain. My mother and father just moved here from Toronto a couple of weeks ago to live with us. And my mom had a terrible fall about 6 months ago. She broke her hip. She's walking with a walker, went through excruciating pain. And what was she given? Any ideas? No, not Tylenol. This was in Toronto, Canada. Oxy, of course. It's the pill they push, right? Oxy is what's gotten the US in so much trouble because of some of the massive side effects, as you can appreciate. So, what I'm going to tell you is a little about how pain becomes pain, right? So, a little bit to get you an idea of sort of demystify the jargon of pain to figure out how the signaling of pain comes to be. How do you, what the pain you feel, what is it? Where does it start? And we need to do that because only when we do that can we start to figure out how to stop. Because there's really, unfortunately, no magic bullet for pain. I wish I could discover it. We're close, but I don't think it's going to be there ever. So pain is no longer a hidden epidemic. This is a piece out of the New York Times a little while ago, and it really tells you that pain is ubiquitous. It's not just here. It's not just in the US. It's a worldwide problem. And roughly 1/5 of the global population, that's billions of people, suffer from chronic pain. And of course, some more extreme than others. And so it's really time for us to do something about it. And as you'll see, much has been done about it, but really nothing nothing really magical or useful beyond for some things. Now, pain is massive, absolutely massive. 1 in 4 people, 1 in 5 people in the world suffer from pain. In the US alone, it has a massive impact on the economy. Not just the economy, the people that suffer from it, the caregivers, the family members, it affects everybody. And sadly, and this really is terrible, for people that have chronic pain, it takes about 7 years for somebody to really be diagnosed and to be potentially effectively treated with chronic pain. And if you look at the last part of this slide, once you wait 7 years, which is an excruciating amount of time with pain, only 1 in 8 will get adequate pain relief. That's terrible, terrible. I mean, it's almost like a stupid lottery. That's ridiculous. It shouldn't be like that. So it's a big problem, and it's getting bigger and bigger as we age, as the global population ages, the US population ages. It's a massive problem. Come on. It doesn't like me. It likes me now. And so the other problem is, so the top, there's a lot of things going on here. If you just focus on the top left, there's a bunch of boxes colored in different regions. And what it's telling you is that for about 10 or so diseases, clinicians have some sort of a formula. Okay, you have this, you're going to be given this. So there's some guidance for physicians to do this. But for the most part, pain is not that simple. What pain is really diagrammed on the bottom part of the slide, which is the landscape of pain. And if you focus to the right side of the slide, what it's telling you is the reason pain is so complicated to come up with something is because it just doesn't affect your hand or your head or your legs. It's a multi-systemic, multi-organ problem. And that's really, I mean, if you can appreciate, that's really hard. How are you going to target something that affects almost every part of your body? How do you come up with something to solve that enigma? And that's really why we have had colossal failures in drug development for pain. Come on. Probably. Gonna have to walk over. Oh, thank you. I appreciate that. Maybe you can help me. So I'll give you an analogy. Back in 2016, President Obama, and I think this was led by Vice President then Biden, kickstarted this Cancer Moonshot Initiative. Their goal was ambitious, but very worthy. What they wanted to do was to eliminate or have cancer in 25 years. Very awesome, really amazing. And I think we've made a great amount of inroads with this program. Why is this relevant to pain? It gives you an example of what then, next slide, please. Okay, great. So in 2018, in President Trump's first term, he took it upon himself to attack pain and set up this thing at the NIH, National Institutes of Health, which is called HEAL, helping to end addiction long term. And this really sort of was catapulted by the extreme escalation of opioid usage and opioid abuse. And this also has an amazing goal, which is to really deal with the national overdose crisis from opioids and to come up with new ways that are perhaps non-opioid in nature so as to reduce the burden that's been, that's coming with these opioid drugs. Next, please. Right. So with that preamble, I'm going to tell you what is pain. Believe it or not, all of us in this room need, yep, I said need pain to live. It is a protective defense mechanism, right? Early warning defense mechanism. It's an alarm. So normal pain is acute, it's reflexive. Next slide. But that's fine. It's the prolonged version of it that becomes detrimental. That's no use. Having pain for long term doesn't serve the body any good, right? So that, and usually that's what kickstarts your inflammation and the repair processes. Perhaps you can deal with it and it will resolve. But what happens is on the right side is what we have to deal with. When pain becomes abnormal, it's non-protective. It doesn't serve any function, any beneficial function. And this is pain as a disease. So this is the chronicity of pain. And some examples are given here. I'll talk more about it. And the goal here, as some of you who raised their hands when I asked about chronic pain, what do you intend to do with those medications? Well, basically to return yourself to a sense of normality where you don't have pain, but are still able to feel, oh, that's too hot, or I burned myself. So you still want to maintain that function, but not have that excessive pain. So without loss of the protective function, but able to sense pain still. Next slide, please. Okay, so just to recap, acute pain is like a alarm system that tells you everything is working well. Chronic pain, the alarm is going haywire. It's just constantly ringing. That's basically it. Chronic pain is just an alarm that just keeps on ringing unchecked, and there's no solution to it. Next slide, please. And here's the other thing, and this is important because I'll tell you some of the animal work that has going to lead to some of these discoveries and why that's challenging and it's not working out. And that is what you and I feel as pain is what I just said, the feeling. The feeling is in the brain. The pain is in the brain. And I'm not saying, oh, it's just something, you're imagining or it's psychological. No. What is happening is the sensory system, whether you hit your toe or you break a leg or as my mom did her hip, that sends signals up through your spine into the brain. And it's not until it reaches the brain that the body registers it as pain. And why do opioids work so well? Because what they do is they kill that signal that goes to the brain. So you still have the pain, but you don't care. You don't give a crap. And that's the problem. Because that feeling of not giving a crap because you don't have pain anymore will want you to have more opioids. That's the problem. So please remember that pain is in the brain. And I don't mean that in a derogatory or a psychological sense. I mean it in the fact that that's what you and I, as sentient beings, as intelligent people, view and see as pain, or the feeling of pain. Next slide, please. All right, a lot of stuff going on here. I will deconvolute everything here. I like to put a lot of stuff as visual guides, but what I want to tell you next is the pain superhighway. All right, so all of you, maybe back when you were in school, learned a little bit of neuroscience or biology, and recognize that, throughout our body, we have skin, we have blood vessels, but we also have nervous system. So these neurons that are the signals that basically is the highway, in the green shown here, the superhighway of pain. And that superhighway works because neurons, the cells that communicate the message from one cell to the next cell to the next cell, from me stubbing my toe or putting my hand or getting a cut in my hand, which sends a signal through these neurons up into my spine, which then takes the signal up into the brain. That's all a relay system. That's the highway of pain. And that's what's sort of shown in this busy slide. And that's what I'm showing here. You have this cut or some sort of a heat stimulus that is very painful. That sends a signal into cells in your skin, which then talk to cells, the neurons, that basically will make this ballet of movement and pass the message on to the next cell, And that's what's happening here. Oh, Please, previous slide. You can just hit the button, like one of the, yeah, go back. Should work. Okay, that's good. So what's happening here is, so it goes from here through your spine. This is base of your spine, and then it goes all the way to the brain. And of course, there's many regions of the brain, but I'm just simply showing that it goes into the brain. How do you feel this pain? Well, you feel it as a stabbing sensation, as pins and needles, or throbbing pain, a dull, aching pain. And this is what physicians, when they ask you, this is what you will describe. Well, what's actually happening is what the process I'm telling you about. The signaling that underlies these feelings happens through this highway. So this is a neuron, an example of a graphic where there's these cars going through. These are the signals. This is the neurons. That's the superhighway. So these cars are shuttling the pain and going faster and faster. Normally, they are moving at a very slow pace, 20, 30 miles an hour. But when you have pain, that signal is like you're going 90 miles an hour. So just imagine that analogy. Okay. So again, no, don't worry about all that, what's going on here. What I'm trying to say here is that until we understand mechanism or how things work, we're not going to be able to solve anything, right? I have a little boy, he's 7. He loves to play with Legos, but he also likes to deconstruct things and rebuild them. And that's what I wanted to show you here, that for many other diseases, we'll take a couple, for example. Let's take cardiovascular. Maybe genetic, maybe my bad eating habits. I'm hypertensive, so I take a lot of blood pressure meds. But why do I take them? I've taken them for 20 plus years now. Why do I take them? Because scientists long time ago discovered key things that were useful in designing those drugs. And here, for example, is an example of cholesterol. Anybody take statins to lower their cholesterol? Yeah, so did I. Painful drugs. They cause all kinds of crappy side effects. But you can do that because you can take a simple blood test and, oh, your cholesterol is up, right? So because of that knowledge that had been acquired in labs across the globe, we have beautiful drugs that have been designed to unmask this scientific, sort of puzzle, and we have drugs for them. I'll take another example, cystic fibrosis. Cystic fibrosis, if you don't know, basically, it's a terrible disease. Basically, it's because of a change in a small part of a protein that causes the person to basically drown in their own lungs. It's terrible, terrible disease. But knowing the mechanism, knowing how this protein works, how this small little mutation in this protein changes the protein, people were able to figure out all you had to do was develop a small molecule or a drug to rescue 5% of the diseased protein. And that was enough to rescue the whole thing. Amazing. But all of that came from a wealth of knowledge, from a mechanistic or a deep understanding of how things work. So that's very important in designing things for pain as well. But we're not quite advanced as these folks are in these different fields. And the right example is of cancer, where it's beautifully worked out. All right. So let's dive in even deeper to figure out how these signals are formed. So here's that man again with his pain in his fingers. Something happens, a signal goes down through those neurons to the superhighway, and you have this squiggly line, which is basically an action potential. This is sort of the code for how the signals are coded so that they can relay to the next neuron. All right, again, this goes through a massive superhighway into your spinal cord, into your brain, and now you have the loop of pain, right? Now, how are these signals generated? Well, they're generated by all these different proteins. It's an alphabet soup of proteins that are critical for making that signal and amplifying that signal. And I'll give you an example of one particular protein that's really exciting and has been targeted for a long time. And I'll give you two examples of these. So again, the same thing. It's the same superhighway, but a lot of different proteins or engines on these neurons that kickstart the signaling of pain. So to take it very simply, you have the beginning of pain coded in by a message. The greater the height of this, the more the pain. It goes through these different regions in your body. As I mentioned already, the spinal cord goes to the brain. But here is where is the beginning of the superhighway of pain. Here in these cells, you will have the right mixture of proteins that are going to drive your pain, both normal pain and unfortunately chronic pain. And this is set up through how they contribute to the amplification of the pain signal. Now, again, very busy slide, but I always love analogies. So many of these proteins control different aspects of the signal, and if they are changed, the signal can be dampened. If they are changed other ways, it can be exaggerated. And as an example, I'll give you this analogy. Anybody know who this gentleman is on the top right? Jimi Hendrix. Jimi Hendrix playing, he's just a musician. You can put Tom Petty, whoever you want. So just playing his guitar with his teeth. All right. Standing right next to him is a big ass amplifier. Okay. So this part is Jimmy playing the guitar, and this part is this whole big piece. So you can stop the signal two ways. You can unplug the amplifier, so there's no music or no pain coming out, or you can simply tell Jimmy not to do, or just snatch the guitar from his mouth, and you can stop him there too. So there's two ways to stop pain, because these two, and by analogy, this is one flavor of a protein, and this is another. This one is the amplifier. This one is what kickstarts the signal, the music, if you will. So if we can understand these proteins, we can probably do something, because these are what start the pain signals. Okay, so why is this particular protein important? Well, this is the fascinating story. So about 25, 30 years ago, in a family in Southeast Asia, it was discovered that these people have basically super amounts of pain. They could go from a room like this to maybe a room that's maybe a degree colder or warmer, and they will have a flare up of pain. And that's manifest in this. This is just not in these two kids here. The feet are completely red. This little baby has one side completely, the rectal area, the hands and feet, the face, all red. It's not a flushing response. It's not the baby is on alcohol or anything. It is excruciating pain. These folks describe pain as if they are in a vat of boiling oil. I can't even fathom what that means. Terrible, right? So on one hand, you have people like that, and you have this woman, Pam Acosta. She lives in San Francisco. She has a change in one of these proteins that make these ions. Normally, they come through, they're important for pain. But in the case where it's changed, so much comes in that super speed highway is going on crack. It's like going super fast. And she cannot do anything. She's afraid to go out. She's afraid to go on an airplane. She takes 50 to 100 milligrams of oxy. That would kill most of us. Seriously. Per day to manage her pain. She puts her head on a pillow and she has pain. It's that painful. Oh, flip the other side. So why is it protein important? Fast forward about 25 years to maybe 10 years from that discovery, another family in England was discovered that had the opposite effect. This young man, I forget his name, I'm sorry, it was in the slide, I forget. This young man has no pain whatsoever. When he was 6 months old, he chewed off his tongue. He has no pain. If he was not wearing what he's wearing, you could see scars all over his body. Why? Because he has no pain. He doesn't know what pain is. Amazing, right? All because in his case, what's happening is the channel that allows these ions to come through that then start the process of pain signaling, that signal that goes to the next cell, to the next cell to cause pain, they're closed all the time. So he has no pain whatsoever. So if you were a big shot of a pharma and somebody comes to you and like, I've got the magic target for pain, this channel, you'd be like, yes, hell yes. Let's put all our money into it, right? And pharma did exactly that. They put billions and billions into this target. And what came of it? Nothing. Because it's not as simple. This protein is not just present in the cells that cause pain, but also in cells that allow you to breathe. That's bad. So what happened was pharma developed beautiful drugs against this, gave it to healthy volunteers to test the compound. All drugs are done this way. It takes time, right? And what happens? The people passed out. Why? Their blood pressure dropped. And so you don't want that. You want a drug to relieve your pain. You don't want things like that to happen, right? That's terrible. But again, this is an amazing example of one single gene, one protein that can potentially be the master controller of pain. And so my lab works heavily on this. We have a small company that recently sold one of our compounds, and hopefully those will go and come to clinic to be able to solve pain because we bypass that blood pressure idea, the side effect. Okay, so some more things to tell you about pain. So I told you about chronic pain, also known as neuropathic pain. This is pain that's caused by a lesion or some sort of a disease that may be happening. So if you know somebody with cancer, they're probably on chemotherapeutics, right? Because they want to kill the cancer. But what happens with most of these patients, about 80 to 90% of people with chemotherapeutics, they develop neuropathy or pain, severe pain that lasts even after the cancer drug's been stopped. So my sister-in-law has breast cancer. She's recovered now, uh, and she had a radio chemotherapy and some of these chemotherapeutic drugs, and she developed neuropathy in her feet, severe tingling and terrible pain. So this is one element of neuropathic pain. Affects This is a very severe kind of pain. You can see in the cartoon, it affects all kinds of regions in your body: stabbing pain, burning pain. You're sensitive to touch. You are sitting next to a fan, and the fan normally would be doing nothing, but now it's painful because it brushes against you. Putting on a jacket is painful. So it's terrible. So this is sort of a pain that's suffered by about 10% of people across the globe. And this pain doesn't really respond to Tylenol, for example, as you said. You need serious medication to deal with this pain. So what are some of the medications that are available for neuropathic pain? So anticonvulsants are being used, tricyclic antiarrhythmics. So some of the examples are shown. Local anesthetics, you can't use them for long term. They're more for surgery, more for acute pain, but no long-term benefits. And then what's used a lot are things like Lyrica or gabapentin or pregabalin, which I'm sure you've heard of. And the problem lies in that all of these drugs shown up there in this red or whatever color pink box here, they cause a lot of side effects, dizziness. So if you ever take gabapentin or pregabalin or Lyrica, you take a huge amount of it. Well, what does it do? It'll stop your pain, but it'll make you sleepy. You can't do anything else. Well, okay, your pain's solved, but you really can't do anything. So that's not good either. Some of them have cardiac effects. Some of them the breathing effects I told you about for the protein that was up and down, mutated, pain or no pain. So there are a lot of problems. And really, I mean, that's not a bad number, 50%, but you want pain relief for everybody, not just for a select few. Why? That's not fair. So I think we're not quite there in terms of solving the pain dilemma. Um, there is hope. All of the wonderful research that has happened in the past, I don't know, 25, 30 years. So FDA, about this time last year, approved a new drug that's non-opioid. So a company called Vertex out of the Bay Area in the US developed a compound called suzetrigine, which is this pill here. And it took a long, long time to have this. And this is one of the first FDA approved drugs in the last 25 years, as the slide says. And so it's sold under the brand name Journavax. You can take a picture, of course. Um, and it's right now sold for acute pain. We have good things for acute pain, so I'm not really convinced that this is going to be useful for chronic pain. But physician friends of mine have started to give it to as off-label to people with chronic pain, and about half of them it works. And what does this guy target? Well, it targets the big ass amplifier. That protein is this protein right here. It's basically opens and lets these ions go through and they start the process of pain signaling. And what this company very cleverly did was to find out exactly where it kind of targets and develop this really very selective drug. It has very few side effects, some itching, some muscle spasm, some rash. But honestly, if you have really chronic, like terrible pain, I think those you could live with, right? So this is something that is marketed since February of last year. So I think it'll become more and more useful. But again, I think this company will develop additional drugs like this that are non-opioid in nature. So you don't seek that reward that the opioid gives you. So I'm very, very excited about this development. All right. So here's the problem. Who's got a couple billion to spare? Because I would love some to develop drugs. Nothing? All right. Let's move on. So the compound I told you that we're just about to sell to a company, we've been developing for 17 years. So the typical journey to develop a drug that's going to come to clinic, to humans, to us, is about 15 to 17 years. So look at this. Cost 2.6 billion. That's on the low end. You start off with, hundreds of thousands of compounds. You select maybe 10,000, and then you start to do extensive work on maybe a couple hundred of those. From there, you select for clinical development because now the costs are in the billions. So you select only a few. Already look at the triage, how the funnel is becoming smaller and smaller, right? So some of these will fail, some may work. You send it to the FDA, and if you're lucky, one gets approved. And that's for example, the one I told you in the previous slide. So extensive amount of research and then clinical research and clinical use needs to go into developing this. And you can see sort of the breakdown of what's happening down here. About 7 years here, 7 years here. You have to recruit patients, figure out which population you want to help. It's terrible. It is a long process. And what's not on this slide is that 99.5% of this process fails. 99.5. What the hell? That's ridiculous. We as scientists have not done a good job, but it's extremely difficult. And the difficulty arrives from the fact that pain is such a complicated problem, right? And this also is true for cancer and other things. This is taken from an example of a lupus slide, and they have made some good success in that, or good inroads into it. But generally, this is what is happening, and those are staggering numbers. And sadly, which is why some of the companies charge so much for these drugs, right? Because they want to recoup their costs and maybe invest into other R&D efforts to make newer drugs. But again, this is the pipeline. Okay, let's bring it back into the lab. Why is that important? Let me tell you a little bit. I know you may not know this and may not care, but you should care because any drug that's developed has to be tested on animals first. They can't just test it on us. No way, not happening, right? So how do we test? I can go around and ask you, hey, are you in pain? Can you describe your pain? I can't do that in a rodent, in a rat or a mouse. I can't. I just can't. That would be kind of creepy and weird. But so what do? We can take these animals and use them as a proxy to study pain. How do we study pain in these animals? Well, if I come to you and if you're in sort of neuropathic pain, if I press on you, you'll say, oh, that's annoying or that's painful. The same thing with an animal. When the animal, it stops exploring, it'll sit down, and then you can kind of just prod the animal with hair-like filaments, gently, little bit harder, a little bit harder, till a point comes where the animal says, or will basically withdraw its paw because it's annoying or painful, right? That's a proxy for pain. You can do the same thing with heat. If I come at you with a laser or heat stimulus, you're like, oh, that hurts. We can do the same thing with an animal. Heat stimulus, 1 second, 2 second, 3 second, 4 second. And at some point, the animal's going to be like, oh, that's going to burn. I'm pain. It withdraws it, right? So, so that's the kind of things we do in the lab to look at. And we can also do that with the cold. So some people are cold sensitive that elicits pain. So we can do those kind of things. Now, pretty obvious slide. We are not rats. Well, we are probably related to monkeys more than rats, but they're not the same. One is not like the other. Clearly, as you can see, the brains are very, very different. But amazingly enough, there are so many things that are common between them. The pain pathway, the signaling pathway, the protein, they're very same. They're very same. There are mutations that exist in humans, they also exist in mice or rats or monkeys. So we can use that information. Obviously, as I told you, we can't experiment on humans until we have the most safest compound that is ready to use. So we have to use proxies like these animals, the rats or the mice or the macaques or the apes, the monkeys. And also across these species, including us, there are motivational behaviors that are similar. There are reward mechanisms that are similar. So really we can use them, and really we don't have any other options but to study them in these systems. So one thing that can happen in that pipeline I showed you, if we can find something, maybe we can get human samples, blood samples, tissue samples to de-risk that journey so that we can come faster to a clinic. So that we're doing that in our lab as well. So coming back to the whole point again is the idea that you want to develop analgesics that are pain relieving, that solve your pain. But where do you start? Do you start up in the signaling here? Do you go into the spinal cord? Do you target something in the brain? Where? It's a highway. Where do you stop? So that's the complicated part of pain signaling and developing drugs for pain. What's happening right now is that as I am a big proponent of understanding how things work. I like to tinker with things, figure out, like my little boy, as I told you earlier, will destroy things only to figure out how he can put them back together. That's very important. We need to do that in order to figure out how things are happening. There are emerging clinical tools to be able to do MRIs and scans. I've done some. I'm sure you've done CT scans, MRI scans. So there's ways to assess how the body is reacting in the context of a pain or a pain stimulant. There's also different therapies that are available. There's neuromodulation and all kinds of things you can implant in spinal cord or even the brain these days to figure out to short circuit that hyperactivity of pain, right? To give it either a break or to boost it and somehow to normalize it. But again, we are faced with a lot of drawbacks. We're working with rodents. Rodents are not us. There are so many different pathways and mechanisms. Which one should we target? It's an enigma. And what if my lab finds something else, your lab finds something else, and somebody else in Denmark finds something else? What is the true, real data? What is the true meaning of all of this? There's insufficiency of clinical information, and with COVID, we were in a whole new mess, right? We didn't know what was happening, so there's some other mechanisms at play that we don't even know about. So it's hugely complicated. What we should be doing are things like so obviously it's very hard to get access to human tissue for good reason, obviously. But maybe we can make things that are like organoids. They're your organs, but we're making them in a lab situation so we can model it better. But it's not as bad as you think it is. We're not making like, ears in test tubes or something. Not like that. Nothing like that. It's just to study how things work. Organ on a chip. So maybe use computer models. That's shown in the right part of it. We can also use non-invasive techniques. We can have, stimulation of the brain. I said neuromodulation, for example. Um, the other thing would be great. I was telling you about statins, right? Cholesterol. You have a wonderful biomarker. You have an X amount of cholesterol, you're normal. If you have X plus 100, you're abnormal. You'll be given the drug. So you have a readily available biomarker that allows physicians to say, okay, this person doesn't need a statin, this person does. Wouldn't that be great if we had a biomarker for pain? We are nowhere close. But that would be amazing. So we could really help people. People with fibromyalgia or complex regional pain syndrome, they are labeled sometimes as drug seekers because they're like, oh, it's on your head. It's not in their head, it's a real disease. But if we had a biomarker, we could perhaps avoid that kind of taboo kind of behavior. And then, of course, new things, antibodies, immunotherapy. A lot is being done, learned from the cancer field, which is really doing wonderful things in the context of immunotherapy. And so maybe we can learn from that to develop a strategy to relieve pain. Let's bring it back to opioids. This is why we're doing this. Opioids are a huge problem. This is how we get addicted. You go to a dentist, they give you, you have a root canal, they give you 10 to 30 pills. You don't need 10 to 30 pills for a root canal. But it's a gateway. It is, you probably need not even one. Actually, my mom, when she broke her hip, she was given a lot of oxy. I think she took it maybe for the first 2 days and then she didn't take it. Perhaps because I told her not to, but she said, I don't need it. I'm okay with Tylenol or aspirin. So it does work. But the problem with opioids are, yes, they are pain relieving. I told you, they work. They really do work acutely. Chronically, not a good idea because they are going to result in this reward and dependence and tolerance. And you can see some of the big side effects. In addition to this, constipation. And that, maybe you can deal with this, take another drug to solve that problem to the first drug. But if you take too much, what it does, it causes respiratory depression. Fancy word for saying it's going to stop your breathing. That's terrible. So on one hand, opioids do work, but pharmacists, scientists across the globe have not been able to take away the bad side effects from the good effects. So this is still a problem. I don't think anytime opioids are going away in our lifetime, but I just want you to be aware that they are a big problem um, globally, but largely in the US. Again, a super busy slide just to give you an idea that people have been working on pain for a long time. And there's a huge journey of discovery. Morphine and aspirin were discovered in 1897, so hundreds of years ago, 150 years ago. And there's some other big events that happened, the development of imaging techniques to be able to test people and to see if they have pain or not. There's the example of antibodies that have been developed. There was a Nobel Prize awarded in 1999 to a group of two scientists that discovered one of these signaling pathways that started pain. TRPV1, don't need to worry about it. It's the capsaicin receptor, the chili pepper receptor. So if ever accidentally, if you're cooking with chili, touch it to your eyes or part of your skin that has a bruise or an abrasion, you'll feel pain because of that receptor that was cloned, and they mapped out exactly how the pain originates because of this protein. So amazing things have been done, and we are working on stem cell therapies that could perhaps also alleviate some of these pain conditions. And again, this journey is not complete, and I think we are getting better and better, and perhaps we'll come up with some great drugs for pain. And so again, I'll reiterate to you that pain is multifaceted. It's not one pain. It's not one cancer. There's multiple cancers. Same thing with pain. There's many different types of pain, but they're caused by your genes, changes in your genes, like those two people I showed you examples of that one gene. They're changed by mutations. They're changed by what happens to these signaling pathways. And they're changed by what these days is really becoming clear is the gut, your microbiota. Microbiome is so important. What you eat, what's in your stomach, the contents, they're going to drive and talk to your neurons, talk to the other cells, and go back and forth about, hey, cut the noise of pain. Hey, make it more painful. It's all because of this. So as you can see, a lot goes into what informs and instructs the pain message. what are some of the things that are being used? I told you about opioids that are used, non-opioids. There are psychological and exercise therapies that are used. Acupuncture, I've had it done. And you may say, oh, acupuncture, whatever. I've had it done, had about 10 years, 12 years ago when I was in faculty in Indianapolis, had back pain, couldn't solve it, took opioids sadly, took aspirin, did massage, rehab, nothing. I had a Chinese colleague at the time who was a faculty as well. He said, look, I'm a licensed acupuncturist. Do you want to try it? I'm like, okay, let's do it. And he says, are you afraid of needles? No, not really. So he says, he comes at me with a big needle, puts it in my head. I'm like, oh, I'm like, all right, it doesn't hurt. I swear to God, within 10 minutes, the pain was gone. And it never came back. Unbelievable. Do I know how it works? No idea. But do I care? Yes, because it solved my pain. So on one hand, I've been preaching to you about we need to know how it works. We need to know. Great. But if it works for you, do you care? No, because it's working for you. So really, I do believe in that. There are some other neuromodulation techniques I was talking to you about. There are some antibodies, stem cell therapies that are more sort of research phase, but they're starting to get used for some kind of conditions. All right, so in the last little while, I'll tell you about a center I set up. So I was recruited to the University of Florida from New York City about 2 years plus ago, and I set up a center called CAPToR. And it's really amazing because it brings in many different people from across this wonderful University of Florida with different backgrounds, expertise. And I'll give you a flavor of some of these. And so this is our Assistant Dean of Research, Dr. Bihorik, under whose auspices this was all set up. And you can see a lot of different colleges are already involved in this. You will hear from members of the Price, Dr. Fillingham, and Dr. Yenisel Cruz Almeida. They'll come here as well to give you a talk to you. People from pharmacy, College of Medicine, neuroscience, where I am, and even College of Veterinary Medicine. We have a lot of furry friends. They have pain. So if we can get to help them on our journey to get drugs for humans, why not? So I'm doing part of that as well. I'll show you something later. So the idea, really the mission of the center is up here. The tagline is to pioneer non-addictive therapies to solve pain through all kinds of collaborations that you see where we work on horses, there's some dogs that and some cats that we were working on, and of course humans, of course, absolutely, of course humans. But it all comes from the lab work and the bench work to the bedside in humans. So that's all critical. Give you some examples of people that are doing this. Chris McCurdy is a professor in College of Pharmacy. He has discovered this natural compound called kratom. I don't know if you've ever heard of it. Kratom has been used to solve pain, and his lab and his team has done some amazing work in this context. He's been on the news many times because kratom is so particularly mitragynine, is underused for potentially opioid abuse disorder. So people take opioids, get abused, they get addicted to it, but if you give kratom, perhaps it could alleviate that. So his group is really working to pioneer that. Then we have folks in the College of Agriculture. She's working to harvest things from the natural plants and to see if there's some magical properties in them that can solve your pain. So much more closer to a non-drug-like state, right? My group, I've told you a lot of what we do. I want to spend a few minutes on this thing right here. It's me and my friend, Dr. Mohab Ibrahim in Tucson, wearing green glasses. This will come up again. I will stay as long as I can to tell you about this. So, light therapy. I love the light. I love the sun. I'm a lizard, I told you. Absolutely love it. So, my folks, when they were living in Toronto is pretty bleak in midwinter. Winter's pretty long. There's not a lot of sun. People get depressed. The seasonal affective disorder, SAD, right? You've heard of it. Well, people in the Scandinavian countries have the same issue. And for many decades, they have used blue light as a way to therapy to increase and enhance their mood. So with that thinking in mind, Mohab, he's a physician scientist. He runs the pain clinic in Tucson, Arizona. Beautiful place, by the way. If I wasn't living here, I would live in Tucson. Love it. Beautiful mountains and beautiful weather. Anyway, back to Mohab. Mohab came to me as for me to mentor him, and he said, "Can you help me design something that's non-pharmacological? He doesn't want to use opioids for his patients." So he had this idea of breaking light into different components. So light is made of different colors, of spectra, right? So what we did here is basically break it into different colors and found that green light of a specific wavelength, you can buy from Amazon, $10, Christmas decoration kind of thing. And this green light basically caused pain relief. So we proved this in animals. And then what he did was, okay, great, wonderful, but we're not in the business of solving pain for animals. We want to solve pain for humans. So he recruited a small cohort of 15 women, because most of these were women, with migraine. And in another study, people with fibromyalgia, also mostly women, gave them the green light to take home and told them that they need to look at it for an hour a day. They can do more, but minimum an hour a day. And no using computers or iPhones or phones during that time. You can read a book, you can look at it, or you cook, whatever. But no phones, no extra effects. And believe it or not, 70% of those folks, 10 or 12 of those folks in both the studies, stopped taking any medications. Their sleep got better. Their pain was gone, or much less. The migraineurs, they had migraines 12, 15 times a month. It dropped down to 2 a month. Amazing. So it doesn't work for everybody, but works a hell of a lot of people. So now he's taken this further into a much larger study of about 2,500 people, and we should know the results. But this is something, it's practical. It's not invasive. It's not going to do anything to you. You're not touching it. You're just looking at it. And if you want to know more about it, I can tell you a little bit more. I can send information to you and you can disseminate it. But again, the point of this is that it's not always a drug that you need to solve pain. Maybe there's some other ways to potentially come up with therapies for chronic pain. So I'm hoping this will move forward, and we're working on it. All right. Some other labs that are doing all kinds of fun stuff to accelerate the pace of discovery. This lab works on accelerating how we can basically test drugs in a much faster fashion. Dr. Carl's group is looking at things with people with trigeminal neuralgia, but in rodent models. It's very important and difficult, terrible pain. We have Kyle Allen's group, who is working on arthritis and the mechanisms of arthritis, both in small animals, in horses, and has samples from people that have gone through total knee replacement surgeries and things like that. And they're monitoring that. And so I expect big things to develop in that space as well. My wife's group, my wife's also a scientist. I think she came to talk to you maybe last year. She does all kinds of things that are above my head, but her idea is to not only try to come up with drugs for pain, but also for things like Alzheimer's and Parkinson's. So very, very, very important. And so with that, I will tell you that my lab has focused on this beautiful protein that I told you about that had that gain of function where that person had so much pain and the other person had no pain. So my lab has really singled out our efforts on this protein, which allows these ions to come and then start the signaling of pain. And we now are at a point that we've overcome this side effect of the drop in blood pressure. So I think we are very hopeful, and we're knocking on the clinical doorstep now to get this to humans. And hopefully it'll get there in the next few years. All right, so last slide. I'll wrap up by saying that the center and its efforts are really geared towards establishing a network and sort of an outreach program like this program to educate people about pain, how it develops, to be able to recruit patients to get tissues available so that we can test and de-risk things that have been discovered in the labs across campus, across our collaborative opportunities across the globe, develop biomarkers so we can better predict if you are given this drug, will you react to it better than somebody who doesn't have this biomarker? kind of the analogy of the statin idea. We are using all kinds of cutting edge discovery efforts at our disposal to work and come up with these new medications for chronic pain. And of course, part of this is important to train the next generation of pain scientists, but also to educate the broader community as to what pain is all about. This is very, very important. There was a study a few years ago where patients were given drugs for their pain, but half of the patients were given the same drug, but were given the same lecture I gave you, basically, that you're told this is how pain starts. Believe it or not, the people that were given the drug and also told about how pain originates, they had half the consumption of the pain drugs than people that didn't have the education. So it's very important to understand how your pain is happening. It empowers you. It really, you need to be, because when you're in pain, you feel helpless, you feel powerless. So I think we need to overcome that script. And that's it. This is my beautiful wife. She's a professor here as well. And these are all the wonderful people. And of course, a lot of this work is funded by the National Institutes of Health, whose mission really is to help us and many scientists across the US develop new therapies for various diseases. Our focus and passion happens to be in chronic pain, but there's others that, of course, do other things. This is my company called Regulonics. This is the company that I formed when I was in Tucson, Arizona. And this company is really now poised to hopefully deliver the next new non-opioid for chronic pain. And with that, I will thank you for your attention and stop and see if you have any questions. And don't be shy like the graduate students. Yes. Yes, please.
Hi. When I have pain, I do meditation and relaxation. But when I had surgery, I thought oxycodone was just the best thing. It didn't give me any bad side effects. And I had to argue that I need twice the amount that they prescribed, and I need to take it until the pain stops, and then it's perfect. And I've done that 3 times. But I worry that I'll have to have an argument with a new surgeon because they won't. How do you know who's not going to be an addict?
Absolutely. That's a great question. Thank you for asking that and sharing that story. You're absolutely right. That's a problem. And that's the reason why they're so bad, right? So now you could potentially be labeled as a drug seeker because you want more compound, more of this. So you said it yourself. I would want twice the amount. Already you're think, why would you need twice the amount? Because you want it for longer? But that's what I mean. So what happens is your body adapts. Your body will want more next time. You go to 20, God forbid, or 25. But that's what is going to happen, right? And that's what they're trying to prevent. Because what I was telling you, at a high dose, if you take it repeatedly, what is going to happen beyond the constipation and other side effects? The slowing of your breathing and the stopping of your breathing. That's the problem. But I completely agree with you. It is very sad that physicians, because of the scrutiny, because of the opioid crisis, are being told, hey, wait a second, you are prescribing too many opioids, so you can't. So they're under scrutiny themselves, so they don't know what to do. That's why I think we need other options. But I fully agree with you, and I'm not being flippant about it. You're right, opioids work, but for short durations. You cannot take them for years on. Uh, you know, yeah. So I appreciate that, and I hope you never have to take them again. Yes, please.
I'll segue from that lady's comments about oxycodone. I think she said oxycodone, or was that hydrocodone?
Hydrocodone, oxycodone. Yep.
Anyway, the same family. Interestingly enough, I'm totally allergic to oxycodone. Hydrocodone works beautifully for me in moderation. But I'd like to go back to your comments about acupuncture and chiropractic intervention. I've had remarkable success with both of those interventions. And again, like you, I can't explain acupuncture specifically. I've read a lot of literature. But my question relates to chiropractic intervention Is that perhaps aligning the pathways or preventing blockage in the pathways? And is that perhaps why that works effectively for a lot of us?
Right. Thank you for that question. So the question is about why things like chiropractic approaches work. You're absolutely right. It's realigning the the pathways or to trigger the activity in pathways that are perhaps gone silenced that would normally have counteracted the pain signaling pathway. So absolutely to basically energize them and to awaken them from their slumber. And that's the best way I can explain it. But I can tell you that the NIH is actually spending a lot of money now to try to understand how those pressure points, what are they doing? Obviously, that cannot be done in rodents. That has to be a human study. But you're not going invasive. You're topical, right? Your pressure points. So you can do that while you're in a scanner, in an MRI or a CT. So while something is being done to you, perhaps a joint, perhaps something on your foot, you're now beginning to see what's happening in your brain or in your spine through that imaging-based method. So absolutely, I think we shouldn't dismiss something that we don't know because it may work. Green light, chiropractic, acupuncture for me. So thank you for that question. I absolutely agree that I think we need to move we cannot just depend on drugs. There has to be something else. Of course, drugs have their utility and they do work, but I think if we can augment that with something like meditation, laughter, yoga, green light, I think it'll go a long way. Thank you. Yeah.
Hi, I'm familiar with a couple of non-medication. Dr. Abrams, UC San Francisco, uses lion's mane mushrooms to prevent neuropathy during radiation. And if they don't give it to them, and then it can be used afterwards, but it has to be continuous afterwards and gets rid of most of the neuropathy. And also in I think it's University of Texas Women's Cancer Center, they use astragalus and cat's claw afterwards. Are you doing with those, or I don't know, or things like that?
Yeah, thank you for that question. So you're right. There's such a richness in the bounty of nature. Whether it's mushrooms, whether it's things from the ocean, from jellyfish, from cone snails, many things are yet to be discovered. But things like what you're saying, psilocybin, mushrooms, absolutely. Cannabis, for example. I don't know. I know it's not legal in Florida, but it has utility, and more so for older people than for younger people because the nervous system is still developing. So you don't really know what's going to happen if you use it very long. So absolutely, things like this are being discovered. And the other benefit I will tell you is, even if they have some side effects, even if opioids have some side effects, what if you take a little bit of my drug and a little bit of opioid that causes no side effects? You mix them together, now you see a huge effect. In fact, that's what we've seen in animals. So when we made our drug for that channel, for that protein, what we found was that if we used a dose of opioid that had no value, pain relieving value, mixed in with a low dose of our drug, which also had no value for pain relief, combined them together, boom, we had a huge effect. So that's the idea, right? And that's important because why? Because that combination has no side effect, but yet it works in addition. So 1 + 1 is not 2; it's like 5 because you have a lot more benefit. So absolutely. So we keep our eye on things like what you just said, the mushrooms, psilocybin, cannabis, things like that can be perhaps combined with something we're developing or we see on the market for us to do this. Absolutely. Absolutely. Communication is the essence of it all, right? That's a little bit trickier. That's a little bit trickier, right? You don't want to share your secrets. The pharma people, they don't want to share anything until it's ready to be available. And even then, they won't tell you what the drug is. They'll sell it to you for $100, but they won't tell you what it is until their patent expired, and then you can go find out, and then you can make it for a penny because it probably costs a penny. So yes and no. So yes, communication is very important. I go to a lot of meetings. I disseminate the information freely. I make it available to people, but not everybody's like that. This is a competitive field. You have to advance in your career. You have to do this or that. So in principle, I agree with you. Sharing that information is going to be critical in order for us to do this. This is what the HEAL initiative is all about, like the Cancer Moonshot. The whole point is to share, get funding, do the work, but then put it on a platform so anybody can mine it to see if there are so many smart people across the globe. Maybe they can use that information to come up with the next wonder drug. So I agree with you, but again, in principle, it's easy to think about, but whether it's doable, I don't know. Yes, please.
Yes, I'm interested in your opinion about tramadol. It's my understanding it is not an opioid. I was diagnosed with fibromyalgia more than 20 years ago, and I have been on tramadol long term. And I also am on several other kinds of pain medication. But the most important thing I do to keep myself free of pain is to meditate and exercise.
Wonderful. Okay, so but your dose of tramadol is the same every time, not escalating it or changing it to take more than normal. Yeah, so that's great. So exactly what you said, right? You combine some other form of therapy with the medication that works for you. So my opinion would be keep doing what you're doing. And I think you're absolutely right to introduce things like meditation, maybe other forms of therapy, maybe light therapy, maybe yoga to augment the pharmacological or the drug-induced pain relief. So I would continue with that. Absolutely. Correct.
I have a question. I guess it was probably the mid 80s, I was working in a pharmacology lab and they were using cannabis and they were experimenting with pain with rats. And they found it to be incredibly effective. And of course, we know that cannabis wasn't available at that time. But I have two questions. One of them is, do we know what the mechanism of action is that causes cannabis to, well, whether it reduces pain or whatever it is? And then the second is, are we making any inroads into being able to do the experiments that are needed so that we can safely use cannabis in chronic pain cases?
Great. Thank you for that question. So cannabis is a hot topic across the nation. As you can see, it's going through some regulatory processes through some states have said the rubber stamp, you can use it. Some states don't allow it yet. I think cannabis is having a heyday right now. Cannabis we know how it works. It works through receptors, proteins that are targeted by cannabis. The problem with cannabis, at least from one of the problems, is there's such a variety of products that are available, and the components of cannabis, the THC, CBD that are part of it, vary from product to product to product. So that has to be regulated somehow, much like cigarettes were back, I don't know, in the 30s, 40s, whatever. There's a constant amount of nicotine or something. There's a warning label, and that was consistent across where the companies were selling. The same thing has to happen at a national level with cannabis products. Cannabis gummies or cannabis oil, cannabis infused tea or a smoothie or wine, right? But the amount of variability is massive. So we don't really know how to do that, how to overcome that hurdle. But to your question of does it work? Yeah, it does. There are clinical studies that have been done using cannabis products in the US, across other countries. But as far as my understanding, it has not been shown to be beneficial yet to the standard of care. I think more work needs to be done. And of course, you're right. In rats and mice, we can solve pain 6 ways from Sunday. We've solved pain 1,000 times. We've done and dusted. But we're not in the business of solving pain for rats. We're here to solve pain for humans. So I think not enough is known about it. There's still some mystery about how it actually works. We know the pathways, which I was telling you about. We know what it works on, but its efficacy has not been conclusively demonstrated. And partly because of what I was saying earlier, is that there are very different formulations. There's an entourage effect, if you will. There's many, many components of cannabis. Which of those components are important for the pain relieving efficacy versus others that might be causing something else? We haven't been able to parse out.
We can't answer that question until we have labs that are able to use cannabis and be sure that it's the same level of drug in every single one. And my question is, are we making any headway in getting centers set up that can do randomized clinical trials or whatever it needs to be to actually figure out whether it will or will not work?
Absolutely. Short answer, yes. Long answer, yes. Absolutely. It's happening. It's happening across different states, not perhaps in Florida, but it's definitely happening both in the preclinical space and in the clinical space to run randomized clinical trials. Absolutely happening. Because for that to happen, you need the same material to be able to give to everybody, right? So people have been able to figure out how to do that. So those efforts are underway for a few years at least now. And I think as we see in the next 3 to 5 years, we will know yes or no whether cannabis is going to be good. I predict it's going to have some benefits for chronic pain.
So when we were doing research, the federal government would not permit it. We were not allowed to do any research on any of these drugs, including cannabis. Now it is allowed, and so progress will be made. I'm going to ask the last question.
Absolutely.
As I understand it, you have identified the gene at the receptor. It's a sodium channel gene. Have you tried gene therapy? So really targeted to that gene?
Yeah. So the question is, have we tried gene therapy? So great question, right? Because chronic pain is what? It's chronic, it's long-term. So gene therapy is likely to be long-term as well. So why not have a chronic solution for a chronic problem? So gene therapy is absolutely one of those things we're pursuing. So there are parts of that protein that we can take and engineer into a small gene, a mini gene that we can put into a virus that's safe, doesn't do anything, just infects the cells that it needs to infect, and we could do that. So at the University of Florida, gene therapy and all these viruses have been made for human usage, and gene therapy is not there yet, but I firmly believe that, for example, that one channel that we talked about, the sodium channel, is going to be one of the key successes for gene therapy. So I absolutely think gene therapy is on the horizon. But again, think about it. It's going to be probably expensive. You're going to be scared to take it because you're modifying something in your body forever, right? And for me, the big thing is, where's the kill switch? If something goes wrong, what do? With the drug, you take it, after a while it's gone, and the effect's gone. But with this gene therapy, you've modified something in your body long term. So
this question up here. On your list of participating UF groups, I didn't see the UF Health Center for Pain Management. Having recently benefited from pain relieving surgery with that department, I'm wondering why those who are actually practicing pain treatment at UF are not included in your group.
So thank you for that question. They are absolutely included. I apologize for not putting them on the slide. I'm working with the Center for Pain Management. I'm working with Dr. Renee Piscora, who is the Chief of Anesthesiology and Pain Medicine at the University of Florida. And we absolutely are working with them to take some of these therapies and discoveries into it. So I apologize for not putting them on. But absolutely, on the most important aspect are these folks.
And the next question is, are you recruiting volunteers in your research on pain?
Well, thank you for that question as well. It's a little too early until we have something that has been shown to be safe in healthy volunteers. We are not. So I'm hoping that within a year and a half, at the most 2 years, we will be recruiting chronic pain patients.
Thank you, Rajesh, for a very comprehensive talk. We really enjoyed it.
Thank you very much.
Next week is integrative approaches to pain management. So concentrating on breathing. There were some questions here on meditation, exercise, acupuncture. So these are other methods for controlling pain. So next week, we'll hear some of that, specifically breathing, how that affects pain. All for coming.